Okay, so Dilip, now we will start your BARC mock interview. First of all, you tell me your two of the favorite subjects.
Sir, one is the thermodynamics and another one is the heat transfer.
Thermodynamics and heat transfer.
Heat transfer.
Okay, so can you tell me the second law of thermodynamics?
Yes, sir. Second law of thermodynamics states that the direction of the energy flows, and that's the main motto of the second law of thermodynamics. And how the entropy will be representing with lesser, greater with respect to that, we can define the second law of thermodynamics, sir. It is also called a directional law, and for that's different from the first law to second law.
No, there are two. I think there are two statements of second law of thermodynamics. Two formal
Yes, sir.
statements also, right?
Yes, sir. Yes, sir.
So do you know them?
Yes, sir.
What are
One
the
is the
statements? Mm-hmm.
One is the Kelvin Planck statement, and another one is a Cauchy's inequality. And these two statements representing for the second law of thermodynamics.
Okay, fine. So, do you know about the power producing cycles, power
Yes, sir.
producing thermodynamic cycles?
Carnot.
So, yeah. So, okay, you have told that, Carnot, right?
Yes,
So,
sir.
Carnot has the maximum efficiency, right? Among all the
Yes, sir.
cycles.
Yes, sir.
Why don't we use it in practice?
Yes, sir. Of course, the Carnot cycle is the maximum efficiency that we can obtain.
Mhm.
But according to that, in the real time, not able to have the constant required amount of temperature with the ambient, and so that's the main reason of that. And that's the main reason, sir. Actually,
Sorry.
temperature will
Can you repeat? Can you repeat?
uh,
We
actually in
cannot have
the
what?
Carnot cycle there is a fixing of the two temperature limits. It's a fixed terms, and
Mhm.
but in the real time it is not able to possible to have to fix the those temperatures in the fixed manner, and so
Which
that's the reason.
temperatures are those? So if I have an engine, if I have a heat engine, which about which temperature you are talking about? We have
Heat
tell me.
supplying from the source and heat rejected to the sink, those temperatures, sir.
Okay, so the temperature of the source and the sink.
It's not constant actually.
No, if I can maintain it almost constant by some means.
Okay.
Okay, like for example, if I have a heat sink like a big pond or a big lake. Okay.
Okay, sir.
So you see that its temperature will not change that much. So
Yes, sir. Yes, sir.
it can work as a sink.
Yes, sir.
So that is not a problem at all. We can have constant temperature source and sink as well. Okay. So other than that, can you think of any other problems?
Sir, for the reversible cycle, it's a Carnot cycle that we use, and there is an entropy change will be become zero. But for that is the reason. But when according to Cauchy's statement that we know that the entropy change will be zero, and that is only for the reversible process. We obtain the maximum amount of energy. But remaining all the things, the
Entropy
entropy
change of what is zero? Entropy change of or
cycle
the
cyclic. I mean,
so if I have an irreversible cycle, if I have listen to me very carefully. If I have
yes,
an irreversible cycle, okay. So if I move around the cycle and come to the same point, so here
yes.
what will be the change in the entropy?
So entropy is the point function, and it's
Mhm.
doesn't depend upon the any path and which process that we are going.
Right,
And final
exactly.
state there's
So here, if I move around the cycle and come to the same point, what will be the change in the entropy for an irreversible cycle?
change will definitely zero, sir. There is no change.
So, you are telling that for the Carnot cycle, the change in entropy is zero. So that is
Yes,
not
sir.
because it is just, that is not because it is, reversible. That is because it is a cycle, right?
Yes, sir.
Okay. Uh, okay. Leave it. Do you know about the ideal cycle that we use for a steam power plant?
Yes, a steam Rankine cycle we use, sir.
Rankine cycle. Okay. Can you draw it?
Yes, sir.
Draw
Sir,
it. Draw it.
sir, I have a touchpad that I'm able to see the what I'm drawing actually.
Sure, sure. I have allowed it. So you have a touchpad, right? Okay. So just wait. I think here I can start a whiteboard, right? So let me. Mm, you have a touchpad, right? So okay. So let me just stop the sharing here. That is even actually better. So if
Sir,
you have a
I think so. It is visible, sir.
yeah, yeah, it is visible. Right, right, right. Okay.
Okay, sir. Uh,
Yeah, draw
sir,
it.
I'm
Very good.
taking
Yeah.
the
TS plane. TS plane.
I
Okay.
sir. Yes, sir.
Yes.
This is the
Yes.
doom, sir,
Hmm.
and I noted the points later. Mm, So this is the cycle, sir, of steam power plant.
This is the cycle of steam power plant.
If you use the superheater, it will be up to the doom.
Use that. Use
Outside.
that. Use the superheater. So why do we use the superheater? And if we don't use the superheater, then will it be a problem or not?
Sir, basically the superheater is used for the at the same temperature to increase the I mean to increase the pressure. I mean dryness fraction to be increased. So that's why the erosion on the turbines will be reduced and the negative impacts and ADCs will be reduced. So that's why the steam generator, I mean the superheater we use for dryness fraction improvement.
Or dryness fraction increment. Okay.
Uh,
Now
uh,
this. Okay.
increase.
So now just name the points. I mean properly, please. Just name the points properly. Maybe with any other color.
Sir, is it big right now, sir? I will make it
Yes, yes,
large.
it is big. I can see it clearly. That is not a problem at all.
Okay, sir. Okay, sir.
Yeah, do it.
2, 3, and 4. So now you visible, sir.
Yeah, yeah, yeah. One, two, three, and four. Okay. Now you explain me. So just okay. Before that, you just name every point. There are still 2 points untitled. So name those also. That is one, right? That is one.
Okay,
After
sir. This
that,
is
we have a point one A. Okay,
AB.
this is B.
Sir,
Fine,
AB.
fine, fine. Right, right. So now you explain that how many processes we have and explain each of them. What is
Okay,
happening
sir.
in each of the processes?
Sir, for
Yeah, one, two, A pump work. So what I mean, so what kind of pump work is this? I mean, so you have to tell me that which process is this? One to A, which process is this? What is
1
happening?
to 8.
What is
Sir,
happening here?
actually, the flow work of the fluid will takes place, sir. For
No, no,
neglecting
no.
the
Like, like for example, we have isobaric, isochoric, isothermal ones. So like,
isentropic process.
so this is isentropic, right? Okay, fine. So this is what. So this is isentropic work addition, right?
Yes, sir. Yes, sir.
Or isentropic compression. Okay, fine, fine. Okay,
Sir, I'm assuming the work giving as a negative.
fine, fine. Now what is so why are you saying 2 to 3? Because there is A,
Sir,
there is
I
A to
changed it
2.
right now, sir. Okay,
No, no,
okay.
there is one thing like A to 2 also.
3 to 2. Sir, it is closer to the saturation curve and it's not that much differ. And so that's why, sir.
But still that is a point, no?
Yes,
No,
sir.
no, no.
But
That is an important part of the I mean Rankine cycle. You so what is actually happening? here from A to 2. Like you have told that from B to 3 we have superheating. So for A to 2, actually what is happening? Can you tell me?
Sir, I'm not recall at that with this moment, but
Okay,
I
okay,
think
okay, fine, fine,
that's the works. What
fine.
sir? That was okay, sir.
So you tell me 2 to B. Okay, boiling, phase change, these are okay. But you have to tell me, okay, T equal to constant. So no, here actually, I mean, what is happening? Either we are extracting heat or extracting work at a constant temperature or at a constant pressure. What is happening here?
Actually, heat supplying, sir.
So heat supplying at constant what? At constant temperature or any.
Constant pressure and constant temperature.
Okay, then from B to 3, B to 3, what is happening? But
Superheating, sir.
yes, superheating is fine, but you have to tell me that what is the name of the process? What is happening thermodynamically? See, what are you telling is the generic things like this. Yes, superheating is happening. Okay, pressure constant, then heat addition, right?
Yes, sir.
Okay, then 3 to 4,
Workout isentropic expansion,
isentropic expansion, fine. Then 4 to 1,
turbine work, positive.
yes, fine, fine,
And
fine. 4 to what?
4 to 1 is condensation.
At condensation is okay, but what is the thermodynamic process? Yes, right, right.
Um, Temperature is constant and same pressure is constant, sir.
Okay, so Dilip, you take for an instance, okay, my point 4 is outside the saturation dome. Okay,
Outside
for
of the
any,
saturation.
yeah, for any particular Rankine cycle, my point 4 is outside the saturation dome. Then what will be the 4 to 1 process? Will it be the same thing like the condensation at constant temperature and pressure for 4 to 1? If my 4 is outside the saturation dome, still will it, I mean, will you describe the 4 to 1 process by the same thing?
Okay, sir. Actually, this is definitely in the below the saturation curve, and I
No,
do
no, no.
not see.
What I am telling is so that, okay, so you have superheated it so far that the isentropic expansion has brought the point 4 outside the saturation dome. It can happen.
Uh,
It can fairly happen. Okay.
so
Yeah.
like this, sir.
Like this. Yeah. Maybe. So now you tell me that for I mean 4 to 1, what is the thermodynamic process?
This is the new point, sir.
Yeah. New point. Okay. Okay, fine. This is the new point.
4 dash, I will name it.
4 dash. So you tell me that for from 4 dash to 1, what is the thing? What is what is happening thermodynamically?
Uh,
Is it constant temperature heat rejection, constant pressure heat rejection, constant volume heat rejection, or heat addition? Anything? You
Sir,
have
it
to tell me.
seems, sir, I'm not sure about it, but it seems to be
Mhm.
constant temperature heat rejection, sir.
Okay, fine. Okay, okay, leave it. And now we will move to heat transfer. Okay. Take a new page. Take a new page. Clear? Okay. So now, Dilip, you draw a cylinder, vertical cylinder, vertical cylinder. Okay.
Oops.
Okay. So now, uh, now around the cylinder, you have first still air at 20 degrees Celsius. Around the cylinder, outside the cylinder, you have air, still air. Okay. The the air is actually not flowing. So
I mean, okay, sir.
still air,
Okay, sir.
quiescent
Clear.
air, yeah, at 20 degrees Celsius. Okay, okay. And now inside inside the cylinder, you have a hot fluid at 60 degrees Celsius.
Okay, sir.
Okay, fine. So now you have to, okay, so now you have to draw the temperature profile from the wall of the cylinder to the to 2 meter outside, 2 meter outside. Okay, so if you draw, yes, yes, yes. If you, yes,
This is the sir.
yeah. So you put any point on the wall of the cylinder, any point. Yes, yes. Take any point. Yeah.
These points.
Okay, this point. Then you draw a coordinate axis outside to that.
Sir,
Draw a straight line passing through that point outside to that. Leftward you have to draw. Okay, wait. Now,
the right side, sir.
okay, I will present now. Okay, so just I will show you for the clarity.
Yes.
Okay. So um, can you just stop sharing? So just I will give you the question. Yeah.
Sir.
So now I will share. So here, okay. So okay, you can also share. Okay. So we will do it simultaneously. Okay, share. I
Yes.
hope
Okay, sir.
so. You see that if you are, uh, I mean, getting the option of sharing or not. Okay, fine, fine, fine. So you first see my screen. Can you see it?
Sir. No, sir. No, sir. I can stop and first of all, I see that this.
Okay. Can you see it now?
Yes, sir.
Okay, fine. So what you have drawn is sorry. Yeah. So you have this cylinder, right? So if I have the, I mean, coordinate axis like this, so this is my x. So
Oh,
from this point, so at this point, I am having the temperature as my T equal to 60 degree. Okay. And I have already told you that my T ambient is 20 degree. So you have to draw along this x-axis the temperature profile. So this cylinder has a radius of 1 meter, and you have to draw the temperature profile up to 2 meter. Now you draw and show me.
okay.
Okay. I am stop
So the
sharing. So I am okay. Okay, to draw.
sir, the fluid is stationary, right? It's not
Yeah,
moving.
yeah,
Sir.
yeah.
Okay, sir.
The fluid is stationary. Okay, first you draw. Okay, okay, okay. The fluid is stationary. Both the fluids are stationary. Then you draw.
Sir, I remove this one.
Hmm.
Sir, uh,
No, no, not inside. Not inside. You have to draw outside the cylinder.
it is outside the cylinder. Okay, sir.
You have to draw it outside the cylinder. Yes.
It seems to be like this, sir. For these 2 meters, it prequel is look like this, sir. This is 20
So you
degrees
have
centigrade and
so you have considered the, okay. So explain it. Why it will be like this? Why the nature of the curve will be like this?
Sir, here is the 20 degrees centigrade fluid is in the ambient
Mm-hmm.
condition, sir.
Mm-hmm.
When it come to the closer and there is a 60 degrees centigrade, definitely it should be greater than the 20 degrees centigrade. And so the profile will be seems to be like this, sir.
Okay. Now if I put a fan vertically, so again you just can you see my screen again?
Wait, sir. Okay, sir.
Yeah. So now if I just put a fan here like this, so this is a fan. Okay. Now because of this, I have an airflow like
Yes.
this. So previously the air was still. Now I have the airflow. Now you draw the same profile on the same plot.
Okay, sir. So uniform velocity, I'm assuming.
Yeah, you assume uniform velocity. That is fine. No, no, no. Wait. You are okay. Assume. No, you cannot assume uniform velocity. Okay, still okay. Okay, you assume. Doesn't matter. You assume uniform
Okay, sir.
velocity.
Sir, I'm from the Prandtl number represents that del by del t power n representing the relation of the boundary layer, and from there itself we can easily identify, sir. Prandtl power n equal to del t equal to del. So it's depend upon the hydrodynamic boundary layer, and for the hydrodynamic boundary layer is inversely proportional to the velocity.
Can you draw it
So, yes, sir. I draw.
without? No, no, no. Let it be. Let it be. You have to compare these two profiles. Let it be. Yeah.
Okay, sir. Okay, sir.
Now, without any mathematical calculation, just by your physical understanding, you have to draw it.
Okay, sir. So I think the slope will be decreases, sir.
Slope will be decreased, but you have drawn something else. You have drawn that the slope has been increased. You see, the slope for the
Oh, okay. Okay,
blue.
sir. Yes, sir. Oh, wait, sir. Wait.
Mhm.
Wait, sir.
Yeah,
Yes, sir. Slope increasing, sir. Sorry, sir.
slope increasing. That means at a particular x, the temperature will be lower.
Yes, sir.
Why?
Because of the velocity increases, it will be propagate faster. So thermal boundary layer will definitely decreases, sir, in this profile, like such a way like this. So that's why I'm putting the ambient condition as closer as possible.
Okay. And one more thing, you see that the distance is 2 meter. Okay. So can you tell me that what is the general thickness of the thermal boundary layer for this case? How much thick it can be?
So we have to take here index n as 3 because of the constant temperature of the surface.
Just from your physical understanding, compared to
Physical.
2 meter, what can be the order of the magnitude of the thermal boundary layer? Like, will it be of the order of millimeters, centimeters, kilometers, meters? What
Yes, sir. Indefinitely it is in meters, sir. With
will be
respect to the
in meter? It will be of the order of meter. The thermal boundary layer, can have the thickness of 1 meter.
Not in 1 meter. I'm telling the units is 1 meter meters. I'm taking.
Not the unit, because unit C, unit, I mean, you can take anything. I mean, if it is 1 meter, you can write, you can always write that is equal to 10 to the power minus 3 kilometers.
Okay, sir.
What is the order of magnitude? Order of magnitude means if I say that what is your height, you will say that approximately 5 feet, like that.
Okay, sir. Okay, sir. Okay, I can understand.
You have to give me an estimate.
Sir,
Simply
definitely.
last question.
Thermal boundary layer for the forced fan is less compared to the naturally happened, sir.
No. I am asking, give me an estimation of the value of the thermal boundary layer.
Estimation, it's going to be not,
Like,
sir. I'm without calculation, it's not able to estimate. I think so.
okay, fine. So here your interview is over, Philip. Okay. Now I will first give you the feedback. Okay.
Okay, sir.
So do you want me to turn off the, I mean, recording, or I can still do it?
Give
When
the
I have
feedback, sir. Then I'm asking the
okay,
questions. Then I have to drop.
okay, fine. So you first see towards my screen. Okay.
Okay, sir.
So
Great.
yeah. So first of all, Dilip, you have to understand that in BARC they are not interested in the formal things, like very formal things that you know that the, I mean, what is Clausius statement, what is this, that they can ask, but very, I mean, occasionally they will ask. They will ask the basic things. So for the, I mean, Carnot cycle, you are actually uttering very official terms, very much, I mean, sophisticated terms, entropy, this, that. But you have to understand that achieving the internal, I mean, reversibility is very hard. That is that is one of the main, I mean, reasons because of which we don't use the Carnot cycle. Okay, that is one
Okay,
of
sir.
the main reasons, and you have missed that. Okay. Other than that, what you have told, that is also the heat transfer at constant temperature, that is also very hard to maintain. Okay. Sometimes, not always, sometimes. So what you have told, that is wrong. You have told that I cannot maintain the source and the sink at the same temperature. That I can maintain. But the temperature at the interface, that is very hard to maintain at a same, I mean, at a same temperature. Okay.
Okay, sir.
So these things you have to understand. You have to study. I mean, I think you have studied well, but you have to understand well. Don't just mug up the things that that this is the definition and this is entropy and all those things. No, understand the things from the very basics. There are also other. I mean, there are also other factors due to which we cannot use the Carnot cycles, but these are the main factors. One of them is reversibility. Okay.
Okay,
Then
sir.
in the Rankine cycle also, you have to understand, if I draw the Rankine cycle very quickly. Okay. So then, okay, so these are the main points. 1, 2, 3, 4. You can write A, B. So this from 1 to 2, this is the constant
Boiling.
pressure, constant pressure heat addition. This is the name
Heat
of the
addition. Yes.
process. Okay, from 1 to 8, this is called the preheating. This is called the preheating. Okay,
Okay, sir.
okay. Now here from 2 to 3, you have identified well isentropic heat addition. From 3 to 4, this is mainly constant pressure heat rejection. Constant
And
pressure heat rejection.
heat addition.
So that is why I asked you that if this 3 is outside the dome, then what will happen? Again, it will be same, the constant pressure heat addition. Sorry, heat rejection.
Rejection.
And
Rejection.
from 4 to 1, isentropic work addition. That is perfectly fine. Okay. So there can be more advanced level question, but due to the lack of the time, I could not go to them. But please study each and every process of each and every cycle. Not each and every cycle, just the important ones like the Rankine cycle, the Brayton cycle, Otto cycle. Okay, mainly they will ask you from either the Rankine or the Brayton cycle. Okay. Now, if I come to the heat transfer, again the same mistake, Dilip, that they will not ask you any kind of formula. They will ask you to draw the graphs from your physical understanding. That is very important. Okay.
Oops.
And the order of magnitude of a boundary layer, a thermal boundary layer, is typically of the order of millimeters or max to max centimeters. So, if this was the thing that this is my 2 meter, then my curve will be something like this. The variation then a constant. So, this will be my delta t. Okay.
Yes, sir.
So this shows that can you feel the things? Okay. Okay. So this is the main interview feedback. Okay. Now I am stopping the recording. Now you can ask your personal questions. Okay. Just wait. Uh,